Hello everyone, good morning. I'm going to talk about variance and types. I am Asjad Baig. Here's something more about me. I'm an application developer at ThoughtWorks, and I'm trying to connect the dots between the functional programming and category theory. Still on this voyage, really been a great joyous one. I'm on Twitter. That's my Twitter handle, AsjadSB. So what will we discuss in this particular talk? Type bounds and how we use that in variance, then variance at its type, list of substitution principle, furthermore the function trait and how it is related with variance, and how the Scala compiler has certain checks in order to ensure variance. Alright, let's move further with types and type bounds. So we have a condition here, A and B both are types. So if A is less than B, it suggests us A is a subtype of B. Whereas if A greater than B, B is a subtype of A. Or other way around, if you want to look, A is a supertype of B, just a vice versa statement. Let's start with an example of an animal kingdom. So we have a class animal, then cat, dog, elephant, they all extend animal, and we have refined dog furthermore with its breeds like greyhound, doberman, and bulldog. So before going any further with the animal kingdom, let's look into the type hierarchy of Scala. Before going any further in the type hierarchy, there's a disclaimer I want to share with you all. The diagram for representation purpose and illustrations, I have restricted only few types, but there are more types like unit, float, but for making this very understandable and all that, it's just restricted to this one. So without any further ado, let's go forward. Here we can observe nothing, and it is at the lowest position. Furthermore, it is observed and can be inferred that it is the subtype, like the lowest type, and everybody is a parent to it. Moreover, if you look at any, it's complete opposite of nothing, isn't it? A supertype of all the types. So it's like a parent to everyone. And let's, for example, consider an int and a list. If we observe it correctly, yes, they are parent to nothing, but any is their parent. So this is the way the type hierarchy of Scala looks. Now let's dive into our animal kingdom type hierarchy. So here we have animal at the top. Dog, cat, and elephant is the subtypes. Then bulldog, doberman, and greyhound, the breeds of dog. So let's talk about the lower bound. It has been denoted as A greater than bulldog. Range of possibilities A can have now is the supertype of bulldog is dog, then animal comes, and definitely any, and we have missed one, that's the bulldog. So all these four possibilities are possible. Upper bounds, so A is a subtype of dog, so dog at the top and all the other breeds at the lower end. So in that sense, doberman, greyhound, bulldog, and nothing, as well as the dog. And there is this multi-bounds. We are kind of restricting the values of A between the two types. As we can see here, animal is greater than A, as well as A is greater than the bulldog. So definitely animal will come and bulldog will come, and the supertype of bulldog is dog. So all these three are the possibilities. Finally, variance is arrived. So Scala supports subtyping, what this statement refers to. So, if there is a subtype relationship and there is an expression which takes a kind of a supertype, the expression should also take a subtype. By that, I meant if there is an expression taking animal, that expression should even take the cat, because cat is a subtype of animal, isn't it? Now, let's talk about variance. It refers to how subtyping between more complex type relates to the subtyping between their components. By the way, this is the definition from Wikipedia. And if this definition is not able to understand properly, we have a diagram to even suffice our needs. So, elephant is an animal. List of elephant, list of animal. There's a question mark because we don't know what's the relation. Let's call list of elephant as a complex type, and we want to understand what kind of a relationship the relation is between them, and variance will help us in understanding this. So let's go further and we will be able to decipher what kind of a subtyping relationship is there for this complex type, whether it is preserved or not. Let's look into it. Types of variance: covariance, invariance, contravariance. So before going any further, let's go with the precondition that we have right now. C of t is a parameterized type, and A and B are the types, such that A is a subtype of B. So let's start with covariance. So covariance will only be there if C of A is a subtype of C of B. By looking at this, we are able to gauge the subtyping relationship is preserved and is in the same direction. Furthermore, there is a diagrammatic representation to ease with this particular understanding. So, moreover, it has been parameterized with this plus sign, and sometimes it is also called as type notation, so don't get confused with this. And with an example as a concern, most immutable Scala collection are covariant in nature, as well as in this particular talk we will even consider list, which is covariant in Scala and immutable, and we will understand an add operation again, but little later. So what we meant by same direction: as you can see, elephant is an animal, and list of elephant, logically it seems correct if we call list of elephant also is a list of animal, isn't it? So if you observe, the subtyping relation is preserved, as well as we can say it's in the same direction. Contravariance now, as the name suggests, we are contradicting. We are contradicting, correct? So C of A is supertype of C of B. This is completely averse to our covariance one, where C of A was a subtype of C of B. As we can observe with this first statement, our subtyping relation is not preserved, but it is in the opposite direction. We will go into the diagrammatic representation soon to understand this opposite direction. Furthermore, it has been denoted with this negative symbol, negative sign. So, for example purpose, we have taken a zookeeper who takes care of the zoo. It has a various function with respect to a particular animal, like feeding, taking care of the habitat, and much more. So, let's say we have a zookeeper of an elephant. That particular person knows about feeding and other activities only related to elephant. But if that person is given an opportunity for some other particular animal, let's say wolf now, that zookeeper of elephant will not be able to do that. So if elephant is an animal, we can't say zookeeper of elephant is a zookeeper of animal, correct? But a zookeeper of animal is a zookeeper of elephant, isn't it? So now if we look at this, it is completely opposite direction, and therefore it is a contravariance. Furthermore, we will go into much detail of zookeeper, how it has been modeled soon. So, class zookeeper, since it's contravariant, negative symbol comes into picture. But there should be some way in which we are able to restrict it to just animals. Thanks to those bounds, we are just restricted it to animals. So let's look into the code. We have this particular feed animal function which takes an animal and returns Boolean. Since it's early in the morning, it is set to false because it's still preparing. So as we can see on line number 4, we have created an animal zookeeper. When we are assigning it to the elephant zookeeper, and when we pass this feed animal with the elephant, definitely we will get false early in the morning. It is working, isn't it? This is how contravariance modeling really works. Invariance. As we can see, C of A is not at all having any relation with C of B. And when there is no such relation at all, there is no need for a sign to be put in the notation. As you can see, there is just C of D. In examples, we will say that mutable collections need to be invariant. Why? Let's have an example. So, arrays in Java, they are mutable, but also a covariant, because of which this thing can be possible. So, as you can see, we create Boolean of string, which means we are creating an array of strings with, its first string is true, second string is false. Then we are making it an object at line 4, and in the later part, we are telling the object 1 should be true. So we are equating it to true. The Java compiler will not give any error, but at the runtime, we will get this exception. Array store exception. So in Scala, we refrain from such kind of a runtime exception. Instead, our compiler is well enough in order to catch this. How? Mutable, and therefore we make it invariant. So let's see here. In Scala, we have cats, an array of cats. We have later on we try to update it with a new type elephant, and oh my god, the compiler is complaining us. There is a type mismatch. We have found elephant, but we require cat, please. So mutable and invariant is necessary. So here is a very good tweet by Rock the JVM. Thank you, Rock the JVM, for creating such a good tweet. It's regarding this producer and consumer concept, and in the part of covariance and contravariance, it's really helpful to look into this. So covariant is when we want to retrieve or produce a type T, and when we want to act on or consume that particular type T, think of it as a contravariant in the type of modeling. This will really help. Liskov substitution principle. So this is a very formal definition of it, and it is possible at first it will not be able to understand, but there are diagrammatic representation of it which will really help. So let's start with Liskov substitution principle and its formal definition. There is a function q which takes an object of x which is of type b, and then if there is a subtyping relation, here a is less than b, then we can prove that an object y of type a can be substituted for function q. And this is much toned down version of that particular definition. Is like if there is a subtyping relation, a is less than b, then every operation that we can perform with type b, we should be able to perform with type a. So let's look at diagrammatically and understand it. A is a subtype of b, and there is a function q which is taking the input of type b, and since there is a subtype relation, we can say we can put type A into function Q. So now if we try to correlate with the formal definition, we are able to, isn't it? So function Q, object X of type B, and there is a subtype relation, then function Q, object Y, type A. So that's what Lexicon substitution principle says. So if there is a subtype relation, we can use that particular type, subtype in that same function. So now function trait. In Scala, functions are treated as object as well as their first class citizen, correct? If we look into the function trait and function 1 precisely now, it is minus t and plus r, which states we are contravariant in the input end and covariant in the output end. I will use this input end as equal to argument and output end to result end interchangeably. So let's start with the function typing rule in order to state whether we are contravariant on the input and covariant on the output. So we have function 1 and function 2. So function 1 is a1 to b1 and function 2 is a2 to b2. Don't worry, we will go through it diagrammatically and example wise and make it very easy. We can state function 1 is a subtype of function 2 only and only if in the input end we are contravariant and in the output end we are covariant. So let's start it with the diagrammatic answers. As we can see, function 2 is a2 to b2, function 1 is a2 to b1, and on input end we are contravariant, so a2 is a subtype of a1. On output end we are covariant, b1 is a type of b2. So with Lexicon substitution principle, we can substitute a2 in function 1 because it's a subtype. So we have put it in, and we will get b1 out as an output, b1 type. So b1 can qualify as a b2 because it's a subtype of b2. Thus we can say we are able to map with the inputs to our output type with function 1. So a function 2 is a specialized one, and we can say that function 1 is a subtype of function 2. Therefore, let's start. Therefore, it's a contravariant on the input and covariant on the output. Let's start with this example. So there is a grass, and its subtype are Napier grass and Coron grass. Napier is also famous for elephant grass, and we have only one vegetarian in our animal kingdom, the elephant, and we are writing a function for elephant. Elephant eats grass, but we have this function 1, which is animal to Napier, and we want function that is elephant eat grass. So function 2, elephant to grass. Let's look at diagrammatically and try to understand it. So function 1 is animal to Napier. Function 2, elephant to grass. Since elephant is a subtype of animal and Napier is a type of grass, as we know, Lexicon substitution principle, elephant can be substituted as animal in function 1. So we do that and we get Napier, which is a subtype of grass, and therefore we are maintaining this particular mapping with the input and the output, and therefore function 2 is a supertype of function 1, and function 1 considers the function 2 cases true, and therefore we are contravariant on the input end and covariant on the output end. So similarly, if there is a function 2 which is having two inputs and a result, that's the definition of it, like contravariant and T1 and T2, and covariant and the R. Now there's a question arises, how an n input function should look. Definitely it will be contravariant on all those n input types and covariant on the result one. But there is a limitation with value n, and this is specific to Scala 2, and it's n equal to 22, but in Scala 3 this limitation is no more, so hooray. Now we will go to Scala compiler checks. Covariant type params can only appear in method result, so it means that if you have a covariant type parameter t, it should be only be present at the output type of the result of the function or the method. In contravariant type parameter, it has a freedom to be in the method type position or the input position of the method. And if you're invariant, you have the freedom to be anywhere. So this particular, there are multiple checks also, but this will be very useful to understand how we try to implement those contravariant and covariant for different functions in that. So now it ring any bell. So the produce or the covariant type, we are producing it, and therefore it's a covariant, and contravariant because we are consuming in the function and therefore contravariant. So let's start with the covariance example list as stated earlier, and we have made it covariant by plus t, and we're trying to implement this add method in it. So element is of type t and we are giving back a list of t. We are getting this particular error by the compiler. Covariant type t occurs in contravariant position in type t of value element. So looking at this, we can realize and analyze what it is because of the compiler checks we have stated earlier. So type t is covariant, and therefore the only position it can be and it's feasible is on the output end. No reason to have in the input one, because input is carved for contravariant, isn't it? And therefore we are getting this. The contravariant position is the input end of the method add. So this shouldn't happen because add is an integral part or integral part of this data structure list. But with variance we couldn't do this. Is there any workaround for that? Yes, type bounds to rescue. As we can see in line number 2, we have stated there is a u type which is a super type of t, and that lm is of type u, and we are returning a list of u. Okay, so let's start with some operations on this list with our animal kingdom. Alright, so let's say we create a list of new, bulldog. So we get a list of bulldog, then we later on add cat and make it list of animal. As you can see, the list type is being, it's updating, it's getting, widened. If you don't get worried with the word widened, we will be able to understand that. Just remember this at line number 2, this particular u is greater than t. That will be very helpful in understanding it. So let's take another example. In this, we have in the same list animal, we adding this particular integer 1. What should happen? Well, let's take the help of the diagram. Int and animal, they have a common super type any. So as we said, u should be greater than t, and therefore we return the list of u. It should resolve to a common super type u. In this case, it's none other than any. So we get list of any. This way, so you can see how from list of bulldog to list of animal to list of any, we tried to widen our scope. So this is widening that happens in a covariant list when performing an add operation. Contravariance example now. So let's say we want to implement a function like record birth for an animal type, which gives a type T. Definitely it should give a type T because the offspring will be of same type, isn't it? But we are getting this particular error. Contravariant type T occurs in covariant position in type T of value record birth. Okay, so in the compiler checks we stated if a type is contravariant, the only position it can be is the method input position or method arguments. In this particular definition, we are even returning this contravariant type T, which is only available for a covariant type, and therefore we are getting this particular error that this type parameter, which is a contravariant, is in a covariant position. Is there any workaround for this too? Thanks to the bounds again, type bounds. As you can see at line number 3, we have stated U is a subtype of T and that animal is a type of U, and we are returning U. We have solved that particular error problem. And when you can see in the later part, when animal keeper is equal to elephant keeper, and later on at line number 8 we are created a mother elephant and we are recording birth for it, and we get a calf elephant, so it's working. So let's infer from all this understanding of this contravariance and all the variance type and what we learned. So this producer and most of the Scala immutable collection we saw, which in sense produces or retrieves an element of type T, are covariant. And whenever we want to model something which we are consuming that particular type or retrieving that particular type, it seems contravariant. Furthermore, we came to know how mutable collection needs to be invariant, otherwise runtime exceptions. And thanks to those bounds that come to our rescue again and again, as we have seen with add and record birth, and as well as how the function in Scala is contravariant on the input end and covariant at the output end. And definitely this function n is limited to 22, n equal to 22, Scala 2, but no more for Scala 3. These are pretty good resources, and not only covers variance but different types of FP that has really helped me. And one is FP Principles EPFL from Coursera, really helpful, and Foundations of P from Julian Truffaut, and Rock the JVM YouTube channel has been really helpful for, as well as Dev Inside You has really good resources even on the Scala toolings, materials and all. I would like to thank all the organizers, and especially Greg Dorrell for his continuous support. Thank you everyone.